This is the BBC.
This podcast is supported by advertising outside the UK.
Thanks for downloading the In Our Time podcast. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello. When quantum mechanics was developed in the early 20th century, reality changed forever. In the quantum world, particles could be in two places at once. They apparently disappeared for no reason and reappeared in unpredictable locations. They even acted differently according to whether we were watching them. It was so shocking that Erwin Schrödinger, one of the founders of quantum theory, said, "I don't like it, and I'm sorry I ever had anything to do with it." He even developed an experiment with a cat to show how absurd it was. Quantum theory was absurd. It disagreed with the classical physics of Newton and Einstein, and it clashed with our experience of the everyday world. Footballs do not disappear without reason, cats do not split into two, and shoes don't act differently when we're not looking at them. Or do they? 80 years later, we're still debating whether the absurd might actually be true. But why are features of the quantum physics not seen in our experience of everyday reality? Can the classical and quantum worlds be reconciled, and why should reality make sense to us? With me to unravel this are Roger Penrose, Emeritus Rouse Ball Professor of Mathematics at Oxford, Faye Dowker, Lecturer in Theoretical Physics at Queen Mary, University of London, and Tony Sudbury, Professor of Mathematics at the University of York. Roger Penrose, can you briefly explain the difference between quantum physics and classical physics?
Well, I think one has to, whatever one thinks really going on in the world, one has to think of the quantum level. That's the level of which atoms, molecules, fundamental particles are to be considered, and the classical level, macroscopic objects like footballs or baseballs or cricket balls, or planets. And there are different rules that we apply to each level. At the quantum level, we adopt a certain procedure known as a Schrödinger equation, which governs how things behave. Classical level, we use Newton, Einstein, various other equations. But this isn't the whole story. Quantum mechanics has another part to it, which is what's called a measurement process, which essentially involves magnifying something from the quantum level to the classical level.
Newtonian physics, as it were, can put men on the moon, and quantum physics led to computers. They both work, and yet they seem to obey different principles, and yet they're both made up of the same stuff. So what's the problem there? Well,
you put your finger on the problem. That is the sense that macroscopic objects in the detector itself, or a Geiger counter, say, is made up out of quantum constituents. So you might think, why don't you just apply the quantum level rules right the way up? And that's where you lead into these problems that you mentioned about Schrödinger's cat and so on, where quantum level rules seem to give you nonsense.
So let's go back to the quantum particles themselves first, Roger, before we move on. Edward Schrödinger developed an equation which described the way quantum particles behave. Can you tell us about the way these particles behave?
I think I should mention a fundamental principle which is part of the Schrödinger equation, which is what's called the superposition principle. You could have a particle in one place and it does something. Or you could have a particle in another place and it does something. Now, according to the rules of quantum level physics, you can also have these things called superposition. So where the particle is in one place and at the other place at the same time. It's what's called a superposition of the two alternatives. So it's what Schrödinger's equation is what's called linear. The fact that these two evolutions proceed completely independently as though the other weren't there is a feature of the Schrödinger equation. And that's what leads to all the puzzles. That's why you have these cats that are alive and dead at the same time, according to the Schrödinger equation.
And this is the stuff that the bigger things are made of. So we've got that. We've got a beginnings of a platform for that. Faye Dowker, obviously we can't see the quantum level. So what was the significant experiment that produced the evidence for what happens at the level which Roger Penrose has been describing? Can you tell us about the two-slit experiment, why it was significant and what it produced?
There are a lot of experimental results which have convinced many physicists that we can't apply classical terms in talking about the quantum world of subatomic particles, such as electrons. And the double-slit experiment, as you say, is one of those key experiments. In this experiment, electrons are fired at a metal screen in which there are two closely spaced and parallel slits or holes. And beyond the screen, on the other side, there is a glass screen, and if electrons make it through the slits, they'll then hit the screen on the other side and cause tiny flashes of light. So when an electron hits the screen, it causes one of these little flashes of light. And if one of the slits is covered up, then the pattern of flashes that you see on the screen, caused by the electrons that go through the other slit, the slit that's not covered, that pattern is quite uniform. It's uniformly distributed over the screen.
Like machine gun bullets going through.
Yes, yeah. But if you uncover the second slit, so now that both slits are open, the pattern of flashes that you see on the screen changes dramatically. So it means that there are regions of the screen that can be reached by electrons if there's only one slit for them to go through. But if both slits are open, those regions suddenly become inaccessible to the electrons. And that's something which is completely at odds with what we expect if electrons really do behave like miniature bullets. So if you imagine that you've got a metal plate and you've got a real gun and you're firing bullets through two slits, through two holes at some target on the other side. And if you cover one hole and you aim through the open hole and you can hit the target, then if you uncover the second hole, you don't expect that you suddenly can't hit the target. But that is exactly what happens with electrons in the double-slit experiment. And
which leads to the conclusion that?
Well, it's one of the reasons that the early workers on quantum theory, they simply despaired of ever being able to describe the quantum world directly. And they made rules of interpretation which say exactly that we cannot speak of the electron in the double-slit experiment. You cannot talk about its properties. You cannot talk about what it's doing. The only thing that we can speak about, are classical objects, macroscopic things like
table,
yes, like I'm banging the table. I often bang the table when talking about quantum mechanics.
And it's never been as flattered in its life, this BBC table, to be called a classical object.
So these are the things, tables, chairs, these are the things we may speak about, laboratory equipment that we use to do experiments on quantum mechanical things. Those are the things we can speak about, the outcomes of experiments that we do, but we can't talk about the quantum mechanical system.
Right, Tony Sedgwick, just to get us up to speed, where are we now? We've got classical physics and we've got quantum physics. They're describing, we believe, the same world, but in such entirely different ways that there seem to be at least two worlds there, and they almost seem to be in head-on collision. Is that right?
Well, that's right. If not in head-on collision, they seem to be hermetically separated from each other. We have the particles, the very small quantum objects.
Which we can't see.
Which we can't see, and as Faye has described, we can detect them. We have evidence for the existence of something, but sometimes that evidence is of a particle. Sometimes it's of a wave when the particle seems to go through both of the slits at once. And the early founders of quantum mechanics thought, well, in that case, maybe we're struggling to describe these things. We shouldn't be describing them as objects like the classical objects. But as experimenters get more refined, this opposition begins to pinch a bit. We find that we can see these objects more directly. We can also do quantum experiments, excuse me, with larger and larger particles. So the distinction between very small objects, which are quantum things, and the real world that we inhabit, which we know how to describe, that distinction becomes... We begin to wonder about where the dividing line, and whether there really is a dividing line. Because the sort of experiments that Faye was describing are now done not for very small objects like electrons, but they've been done for collections of particles making atoms or molecules, or quite large molecules. Recent experiments by Anton Zeilinger have shown this quantum behaviour for large molecules.
It's very troubling to physicists, as I understand it, and it's certainly very troubling to me, that you have the same world, one can keep saying that, because atoms and so on, being described in ways which you say hermetically sealed from one another, but actually they contradict one another in quite massive ways. And Schrödinger himself, who provided one of the basic equations, also provided a comment on the equation in Schrödinger's cat. Is it possible briefly to say why he wanted to put his cat in a box in that way, and what it signified, and what it still signifies.
Schrödinger anticipated the problems that would arise when we extended quantum mechanics to larger and larger objects, like these recent experiments of Zeilinger. Schrödinger didn't believe that the theory was the final word, and he introduced this application of the theory to everyday objects as a reductio ad absurdum, as a way of saying, look, the theory can't be right. You can even invent ridiculous cases, he said, like the following. Let's suppose that we put a cat in a box which is linked to a device which is triggered by a radioactive atom. Radioactive atom is certainly a quantum object, and after a certain while this quantum object will be in one of these superpositions that Roger talked about.
In two places at once?
It will be,
no,
it'll be two kinds of atom.
It'll be two kinds of atom, right.
And if it's one kind of atom, it will have emitted an alpha ray, which will trigger a device which makes a hammer fall on a phial of hydrocyanic acid, which kills the cat. So at this stage, we have the superposition having spread from the radioactive nucleus to the cat and the box in it. And the cat is now alive if the atom hasn't decayed, dead if the atom has decayed. So it's in a superposition of being alive and dead. Real cats aren't both alive and dead at the same time. They're either alive or dead. But Schrödinger said, look, this theory, which he had to take responsibility for helping to develop, predicts that you do get cats in a state like that.
One thing I've been sorry to interrupt you, Tony, but I don't want to I don't want you to get ahead of myself because I'll be lost completely. I still haven't got it clear in my head why so much is made in the notes and the stuff I've read for this programme about the observer changing the condition.
I think you see the different viewpoints here. You see,
so if I look at it, not me, but you three look at something, the very act of looking at it changes what it is.
There is a kind of view that I think Heisenberg tended to promote, which is somehow the observer is influencing the system in an uncontrollable way, and there's something in the action of the observer which has a sort of active effect on the system, and that's what you have to worry about. It's not the way I would look at it. My view is that there's something objectively taking place which it hasn't really got anything to do with an observer. You see, you have say I mentioned a Geiger counter before, a physical object, and that there is a certain level in that physical object at which the rules aren't those of Schrödinger's equation. Something different happens. And it has nothing to do with a conscious being coming along and looking at it. Now, other people might take a different view on this. They might say, well, the crucial thing is when a consciousness comes in and an observation is made, and so somebody is there to perceive a result. So that would be one position you might hold, but it's not mine.
I mean, what we're trying to find out, it seems to me, is several things. First of all, what the quantum world really is. Secondly, if what it really is the reality we really live in. And thirdly, how it affects the reality that we live in everyday life. You have another idea, Tony Sudbury, which is the many worlds theory.
Well, let's go back to Schrödinger's cat. And Schrödinger produced this idea of a cat which was in a superposition state, because we have to take a cat seriously as an element of the physical world made up of quantum things. Therefore, it can be in this superposition of being alive and being dead. But actually, a real cat in the world is interacting with the rest of the world, and it will very quickly interact in different ways, depending on whether it's alive or whether it's dead. If you look at a live cat, something very different happens in your eye to what happens when you look at a dead cat. And this means that the superpositionness of the cat quickly infects the rest of its surroundings and eventually the whole universe. So that very quickly the cat is no longer in a superposition of being alive or being dead. It has no state. It is either alive or dead, as we would expect. But that superposition has spread to the whole of the universe. And we have to say that the universe is in a superposition of one which contains an alive cat and one which contains a dead cat.
So what you're saying is that the many worlds theory is that everything, if we take the quantum principle to a conclusion, let's maybe even risk a logical conclusion, the whole world is in superposition. So there are millions and millions and millions of worlds all the time, but we only see the one that we live in. That you're in superposition, that the listener is in superposition, the microphone is in superposition. There's millions of the things all over the place.
Each of those individual things is not in a superposition. It's the whole universe that's in a superposition.
What does many worlds mean when you're saying that?
Many worlds means that all the different things that can happen in a superposition, although we only see one of them, we have to regard the other ones as real in some kind of parallel reality. And what it amounts to.
So how does it amount? Look, let's take an example from this studio. There's a clock there's Roger Penrose, there's Faye there. Now, can you just tell the listener what superposition in the many worlds theory means in these specific cases?
Well, there's nothing in this room that would put us into a superposition, but let's have Schrödinger's radioactive nucleus triggering a bomb in the corner of the world. Then, like his cat, we would be in... There are two possibilities for our future. According to the many worlds theory, according to everyday ideas of things, one of those things happens. Either we survive or else the bomb goes off. But according to the many worlds theory, there is a universe in which we survive and we're still here happily talking. There's another world in which we are shattered to smithereens. But we must regard both of those worlds not both as being equally real.
Right.
And in superposition, the view is that they're both there at once and...
Yes, well, I was following Milton's instruction to take this idea of many worlds seriously.
We're talking about consciousness as much as measurement here, aren't we, Roger Penrose?
I think the thing is, there's a bit of confusion in that, well, partly confusion because I sometimes talk about consciousness, but the point is that consciousness actually plays a role in all the other interpretations, or most of them. That is to say, what stage do you actually perceive the cat as being either alive or dead? And in the so-called many worlds view, okay, they coexist. There's a live and dead cat and the live cat with its universe and the dead cat with its universe, and they're coexistent. But a conscious being sees one or the other. So one would need an explanation for why consciousness is not allowed to perceive the superposition. So what you really need is a theory of consciousness to make sense of the many worlds theory. Now, my own position is quite different from this. I say you don't really need a theory of consciousness at all. The cat is either alive or dead because it is either alive or dead, not because consciousness is putting it into an alive state or a dead state. So there's different views one might have here. But my own position is that it's a physical process which takes place far below the level of consciousness, and it does depend upon a change in the rules of quantum mechanics as we presently understand them.
So if we ask the question, why do we see one individual, singular world, singular reality, then either it must be that world is real, it's true, and there is the one and the only one reality.
Let's skip to the table. It's not so much a joke. It's very useful. There's only one table. If you lift it up, it drops the floor because of gravity. It has solidity. It obeys the laws of Newton and...
Indeed, as we observe
Send it into space, it obeys the laws of Einstein.
Indeed, so that's one choice. As we observe it, that is the real situation.
So that is an objective reality, you would say?
Yes, or there must be something about our consciousness that means that that's all that we observe. So either you want a realistic theory, which explains why this is the one and only reality, or you need a theory of consciousness. And in the many worlds interpretation, also known as the Everett interpretation, it seems to me that you're denying the one and only one reality of the table being exactly here. So therefore you must need a theory of consciousness, and therefore it is, to me, it's too subjective. Even if it succeeds in being able to reproduce the predictions of Copenhagen quantum mechanics, which I don't think it does, and I'm sceptical that it ever will. Even if it does that, you would still have had to put in a theory of consciousness, and to me, it's too subjective. I think that the history of science teaches us that seeking an objective theory, a theory that's observer-independent, that doesn't depend on subjective notions or on us in any way, that is the most fruitful way to go. That's where progress is going to be made.
And that is what we're seeking. And that is what Everett hoped to produce with his theory. It's not necessarily a theory of consciousness. It's a theory of objects which register the rest of the world. But of course, consciousness is what we're interested in because it's what gives us our experience. And it's our experience that says there is only one world, there is only the table in this studio sitting there and occasionally being thumped. But that's
where the buck stops.
That is in the theory.
Yes.
It is in the theory that there is only consciousnesses which see a table like that.
Right, can I come to your ideas on this, Roger Penrose? To go back to the beginning of the programme, really, we have these two worlds. You have the quantum world, small electrons, photons, you can't see them, they're in two places at the same time, and they behave like waves, and they behave like part of that world, and obey certain laws leads to computers. In the classical world, Newton Einstein leads to men on the moon, aeroplanes, and so on and so forth. These two are made up of the same things that make up everything and all of us, yet they behave in radically different ways. And you have put your mind to trying to find a unified theory. Now, how can you give us, if I've misrepresented you, you will certainly tell me, but then can you go into the sort of theory, the way that you think you can bring these two systems together?
Well, I think, yes, the procedures that we use to describe these small-scale systems and those that we use to describe large-scale systems are both approximations to something that we don't yet know. Now, the question is, what is the level at which something new happens? And when do the quantum rules start to go wrong and the classical rules start to come in? What is the nature of the bridge between these two levels, if you like? And there, I think, the major clue, in my view, is to try to bring quantum mechanics together with Einstein's theory of gravity, Einstein's general relativity. Because general relativity has its own family of principles which are in many respects sort of in contradiction with those of quantum mechanics. And we know they're there. We know that for large-scale systems, for planets, for neutron stars, things like that, general relativity works extraordinarily well. It's a very, very precise theory. Yet at the quantum level, the other end of the scale, we also know we have a theory which works very well, but one must somehow go over into the other at a certain scale. So what I've been trying to think of...
You think it's, just to interrupt for a second, you think it is out of the question that these two could exist independently, so they work okay, leave them alone, it just happens to be like that?
Well, I do think it's out of the question.
Yeah.
I mean, some people might say, well, these are, approximations, we use this one or another one. But the trouble is as I think Tony said earlier, we're getting to the level at which... it's not quite clear what a quantum level object is. I mean, the experiments that Tony referred to earlier of Anton Zeilinger's, where he had these little C60
carbon
molecules,
clusters,
these things called buckyballs. These little tiny objects, which, according to Zeilinger's experiments, do momentarily exist in two places at the same time, because he fires them through two slits, in effect. It is the thing that Faye described. But now for pretty large objects, complicated structures. And the question, is there a limit at which these quantum rules will break down? Now, with certain colleagues that I have in Oxford at the moment, Dick Baumeister, William Marshall and Christoph Simon, they are developing an actual experiment which will test what I regard as the boundary between these two levels. We start to see something new happening. Should I say something about this experiment?
Yeah, do, and then I'll bring in Tony and Faye.
Think of something like a diving board. The length of this diving board is something like the width of a human hair. And the width of the diving board is about 1/10 of that. And you must imagine something bouncing up and down on that little ping-pong ball, if you like, bouncing up and down on the diving board. And the thing is that if you can do this at a certain level, you will start to come into conflict with the principles of Einstein's general relativity, and at that level is where I think you're going to start to see something which is not in accordance with the Schrödinger equation, if you like.
Will gravity play a part in that?
Yes, this is absolutely crucial. It's extraordinary, you might think, that something, 1/10 of the width of a human hair, its gravitational effect should actually have any relevance. But when you do the calculations, you find that this is... Actually, I'm slightly cheating, because this is a preliminary experiment they're doing, which is still about 10,000 times below the level you would need. But if they can do this successfully, it's well on the road.
But would this be a crucial and extraordinary move?
Oh, it's fantastic. That an experiment like this should be done. I think it's absolutely crucially important, because what we've been talking about, what I've been talking about in looking at Everett's theory, is extending quantum mechanics from the very small. Enormously. You might say it was arrogant. It's tremendously ambitious to extend this to the whole of the universe, but so far we've seen no indications that that's not the right thing to do. So it's crucially important to test the limits of how far we can extend a theory. The fact that there have been absolutely no indications so far leads a lot of people, including myself, to think that, well, we do really have to think about this being the truth for the whole universe. But it's so important to test the limits and find out where it breaks down, which is what Roger is suggesting.
Fine.
Well, I agree. These experiments are amazing. I'm staggered that they can even do this preliminary experiment, that they have the technological
There's still a few
capability
years,
to do
yes.
to do it.
It'll be a few years, maybe about 3 years, I think, before we're working. But there doesn't seem to be. I mean, I'm no experimentalist, but my colleagues seem to express a lot of optimism, and they've been up and down. Sometimes they've been pessimistic, but the optimism has lasted for quite a while. So I think it's very likely that in a few years they will be able to do the preliminary experiment.
This is a good example of a case where proposals for theories which will go beyond standard quantum mechanics, that will extend our scientific capabilities beyond the beyond the boundaries of the Copenhagen interpretation. That theoretical proposals like this, lead to experimental tests of quantum mechanics itself. So, in that sense, even if you are a dyed-in-the-wool believer in completely deterministic linear Schrödinger equation evolution,
that was quite a mouthful. No, just congratulations.
As the underlying reality, it's very exciting to hear about these experiments, because the experiments will be testing quantum mechanics.
Just to speculate for a moment, as if we haven't given what came from classical physics, which was enormous advances, quite incredible advances. Given what came from quantum physics, which is enormous and colossal advances in the world in which we live, are what Roger and his experimental team up to, would they lead to similar-ish enormous leaps in the way that the world is conducted through us, the equivalent of putting men on the moon and computers? Would it take us to another stage? Tony?
So have you patented them? What use is a newborn baby? I mean, can you possibly tell at this stage? When people first developed quantum mechanics at the beginning of the last century, they had no idea of the practical implications. So I would be inclined to say that was a premature question.
What one means by practical depends on who you are. So, I mean, for example, if the sorts of theoretical ideas that Roger has been putting forward work, and if they can be made more concrete, then this would be a major breakthrough, in the sense that we could apply this new theory, this new and better theory, better than our fudge, our rule of thumb of Copenhagen. And we could apply it to things like quantum gravity.
I mean, you're asking about implications.
Yes.
First of all, I should say that the things I've been doing aren't yet what I would call a theory. They're ideas and telling you the level at which something new comes in. But I think the major revolution, which I do think we need, would involve a complete rethinking of not just quantum mechanics, but how we look at space and time and all sorts of things. So there will be a revolution waiting in the wings. And when that revolution has come, okay, then maybe we can think about issues like what thought is. I mean, what is it that... I mean, in my view, conscious thinking does depend on this unknown part of physics.
I'm very sorry, we have to stop there. I got carried away and stopped looking at the clock. Thank you all. Thank you all very much indeed. I think I learned a lot. I'll have to go and think about that now. Thanks for listening.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.